than between the first and the second dot, the 45. And so you can continue all the way down. Let me get an X down here by saying these are the speeds. And again, hopefully you'll just be seeing kind of the same thing we've been saying, that this is showing bigger and bigger speeds. That means it's going faster and faster. And the definition of acceleration is the change in the velocity. And so sure enough, it is changing and going faster and faster. Now, this column here won't be so obvious until we start making our graphs. So I'll just follow their directions. Their direction says take with the time and square it. All right, so here's the column for time, 0/30th. If you square it, that means 0 times 0, what do you get? 0. But it's 0.09 seconds squared, right? Because a 30th times a 30th makes 1/900. And they put that in the column for you. So this is in units of 1/900. So we don't have to deal with fractions that way. So they're trying to make it easier on you so you don't have to worry about small numbers and decimals. See, watch, you'll see the same thing here. This, remember, is 1/30th of a second. So if I square a 1/30th times a 1/30th, 1 times 1 is 1. But that's 1/900th of a second. And then over here, I'll just do one more, 2 squared. 2 times 2 is 4. And then a 30th times a 30th is 900ths. And so if you remember your squares, you can just keep going down and list all your squares until you get to the totals of 13 squared is what, 169, 144, 121 as we work our squares backwards. Okay? So that's your job, is to start to fill this in. And let me give you some other jobs that are for you. Once you get this table completely filled in, okay, so you and I just together have collected the data, you're going to now start analyzing it. And so on page, and I think your first one is page 12, here it is. You are asked to make a plot of the average velocity versus the time. So that's where these two columns come in. Here's the average velocity in this column. Here's the time in this column. So put them in here and a pattern will form. Well, I'll mention and say a little bit about the pattern in a second. But then it says go on to the next graph. Okay, so the next graph, I think I said that backwards. This is the second graph. This is the first one. But it really doesn't matter. So I'll go to the first one now. That was actually the second one, the velocity. Here's the first one, page 11. This first one says plot the distance versus time. Okay, so back to our chart. This is why we have this. This is the distance, okay? And this is the time. And so just put in your little dots. Don't do anything with it quite yet. Just put in your little dots. And put in your dots for your third one also. The third one is plotting distance and time squared. So again, coming back to here, here's the distance column here. And now, that's why we needed these numbers, the time squared, to do this third graph. But if you've done things right, they will look sort of like this. Let me go ahead and clear off the board here, because I think you got all that now. And if you have done these calculations correctly, and I should add, if I recorded down the data correctly, and I should add, if the computer equipment worked correctly, we should have a nice pattern. Now, the pattern may be less than perfect because maybe there was a mistake along the way. Maybe the mistake was me recording them. As you saw, I did make one mistake, and I think I caught that one, but there could be another one up here. There could be a mistake in you doing the calculations. There could be a mistake in the spark timer. Like I said, that one there I really question, and I'm thinking the machine made it, so I kind of skipped over that dot and went to the next one. I could be wrong, and maybe the graphs look kind of funny, but here's the idea. The idea is when we do our graphs like this, and should have grabbed a second drying rack. Well, I think it's going to be dry enough. Is you will have one graph that will look sort of like this, dot, 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 dot. And maybe I should have said, don't put in your line yet. First, just put in the dots. Because you may have one that's off a little bit. And that's why we always collect so much data. We understand that between one person, me, being human, making the data, you, doing some calculations, being human, may make a mistake. And then 3, our equipment, which is built by humans, may make a mistake, or it just, just with time, things wear out. And so we know just from experience, there's always something wrong with our data. So we're looking for an overall pattern. If one thing is off, depending on how much it's off, we ignore it or kind of round towards it, and that's what I want you to see. So we're going to then draw what they call a best fit curve. And so if your dots look like that, just kind of do a hand drawing of saying this is roughly what it was supposed to look like. This is what nature was intending. Don't draw from one dot to another, to another, to another, because when you do that, it's kind of implying that those dots are accurate. Those dots are perfect. And what I'm trying to say is we already know between the two of us working and that equipment, those dots are not perfect. But hopefully we have so many dots that the pattern that nature intended shows up. Okay? Your second graph, which is velocity and time, will look something like this. And it should mostly look like a straight line. And if one or two of them are off, just take that as, hey, there was an error made. And so if you were in class face-to-face, I would hold this up and I would say, get yourself a clear ruler. Because the clear ruler allows you to kind of put it on here and kind of eyeball if things are above or below, because all of your dots will not quite be in a straight line, but they will be close enough that we would draw this conclusion, that nature intended it to be in a straight line. Just the imperfections of us humans, okay? Either me, I know it's not you, but it's either me or my equipment made a mistake. And so if those dots are not exactly straight, I don't want to draw something that actually follows the dots. I want to draw something that kind of averages those dots, knowing that there's some mistakes. And statistically, some of those mistakes will be too high and some will be too low. And so if you kind of do what we call the best fit curve, we will get a better graph. Okay? So I got a long one over here, so I'm gonna grab something that's not clear but a little bit longer. And for this one, I would look at these dots and go, okay, that looks like a line, that looks like a line. And if I do this one, and this one's way above, I'll give it some credit, but I think something's just really wrong with that one. Maybe I would do something like this. Oops, I twisted it. But trying to get this one a little below the line, this one a little bit above the line, this one a little below the line, this one a little above the line. And so kind of split that difference. And so that's called a best fit curve. And so that's what we do in nature. You're going to see the same thing on the third graph. The Third graph, you are asked to plot distance versus time squared. And what you'll see is they're really crunched up at the beginning, and because of the square, they spread out and they'll look very much like a line. And so the same idea, do your best fit curve on that one. And so this part of the lab is what we call analyzing the data. So we collected it together, but now you're analyzing it. And in this case, you're analyzing it by, well, doing a few calculations to get the table, but now you're looking for patterns. Because these three graphs, those shapes, those patterns, you are going to use to answer these 9 questions. And so go ahead now and read these 9 questions and answer them. But I want to point out that I think this is question 7, they're not numbered, but it does ask for the value of your slope of your line, because they want you to conclude by the time you get to here that it's the slope of this line right here that is the acceleration of the falling object. And so use your math skills to measure this slope. And the fact that it does have a slope tells me that its velocity changes with time, so that part of it tells me it is accelerating. And then the value of that slope is telling me the rate at which it is changing, and that is the acceleration. And so hopefully that is something very, very close to the 980. Usually in lab we get numbers like 970, 960, sometimes 950. Sometimes even low as 940, sometimes high as 1,000. But if you're in that area, you're doing well. And then one word of caution. A lot of times when students are plotting the slope, which just to remind you from your math class, the slope is the rise over the run. And your run is measured in units of 1/30th of a second. So you might, on this end, have something like 12, and on this end, 0. And it's tempting to say, oh, the run is 12 minus 0, but it's really 12/30ths of a second. Minus 0/30ths of a second. And so your run is not 12, your run is 12/30ths of a second. This is a long way of saying if you get the slope of this and you get numbers in the 30s, like 33, 34, 35, you're missing this 30s. And if this was a face-to-face class, I recognize that right away. I walk around and I go, okay, so hey, what, you guys are finally getting done. What slope are you getting? And people go, oh, I got a 34. I go, oh. Hey, I know exactly what you did wrong. Let's look at your run when you were asked to do the slope. So a little warning there on that. But anyways, answer that. And so I'll call this a wrap, but I just want to say those are your 5 pages, okay? And so fill in those 5 pages, scan them, go to Canvas, and if you have any troubles, shoot me an email or send me a question, and that's it for lab number 1.